So last class we were doing analytical solutions. These are analytical means approximate analytical. So that is what we are meaning by that. So analytical solutions based on weak form. Yeah, so that is what we were doing in the last class. So we discussed how to get the weak form and then how we used to that to solve problems. So now let's take the second example which we have taken earlier. So let us solve that example using weak form. So the second example on this I'm going to take is you should be able to know, given a differential equation, you should be able to use these techniques to find the approximate analytical solution based on these approaches. Any differential equation, although I'm taking some specific examples. So for this, I'm taking the beam problem. So the corresponding differential equation is d2 by dx square ei into d2v, where v is the transverse deflection minus q equal to 0. So this is the differential equation, and let us take the simply supported beam. So both the ends are simply supported. So typically, the stiffeners, if you look at in the ships and submarines, we will have longitudinal stiffeners, circumferential stiffeners. They can be approximated, strangers and rings can be approximated using this. So yeah, this is the distributed load q. This is x coordinate and this is y coordinate. In that direction the transverse deflection is v. The length of the beam is l and its flexural rigidity is ei, and we are taking that ei and q are constant along length. So ei q constant along x. So along with this differential equation, we will also have boundary conditions. So I am just writing BCs. BCs means boundary conditions. So for the given problem, if you see the boundary condition, one is that left end transverse deflection is going to be 0. It is not allowed to move, and also at the right end. So one is that V equal to 0 at x equal to 0. That is one boundary condition. Another is V equal to 0 at x equal to L. That's the another boundary condition. And then we know that the bending moment, because both left end and the right end beam is allowed to rotate freely. So if it is allowed to rotate freely, then the bending moment is 0. So ei into d2v by dx square is going to be 0 at both the ends. So ei is a constant, so we can simply write d2v by dx square equal to 0 at x equal to 0, and d2v by dx square equal to 0 at x equal to L. So out of these boundary condition, if you look at the first two, for this problem we have already got the big form. So we know we have derived the big form. So we have seen that v and dv by dx are primary variables, and if they are prescribed, so those boundary conditions are essential boundary conditions. So in the first two boundary condition, v, which is a primary variable, is prescribed. So these are nothing but set of essential boundary conditions. So these are EBCs, essential boundary conditions. And the last two, if you look at in this, d2v by dx square is prescribed, which is a secondary variable as a force quantity. So the prescription of a force quantity is natural boundary conditions. So the last two are natural boundary conditions. So now for this differential equation, we have already derived the big form. So I'm directly writing here. So we have seen that big form for this problem was w into d by dx of ei into d2v by dx square. Whole thing is evaluated at 0 and L. Then minus we had dw by dx ei d2v by dx square, the evaluated at. So these are the boundary terms, and then plus we had this integral 0 to L d2w by dx square into ei into d2v by dx square dx, and minus integral 0 to L w q dx is equal to 0. So this is the weak form. We have already derived this. So now we want to find out the approximate solution of the problem. So basically we have to assume an approximate solution, and let us say that we want to still assume a solution in the form of a polynomial. So if we want to assume a solution in the form of a polynomial, so now when we assume that, we have to see, because this integral term highest order derivative of v is second derivative, so whatever we assume, it should be differentiable at least twice. So that means a polynomial means a quadratic polynomial. That's the minimum thing. Of course we can always take more number of terms and solve the problem. We will get more accurate solution. So but minimum what we can have is the quadratic polynomial. So now when I assume the approximate solution, so approximate solution for transverse deflection v. V is the transverse deflection of the beam. So v equal to, and we have to have, when we are taking a quadratic term, this means we have should have all terms before that, that is constant and linear terms. So a0 plus a1x plus a2x square. That's the minimum thing we can do. Now before we can substitute this in the big form, the requirement is that we satisfy the essential boundary conditions. So to satisfy the essential boundary conditions, that is the first two boundary conditions. So we are only looking at the essential boundary conditions. So if we look at the essential boundary condition, one is v equal to 0 at x equal to 0. So this implies, now if you put v equal to 0 in this expression and at x equal to 0, so this term would be 0, this term would be 0, so you will have a0 equal to 0. That is one. The other condition is v equal to 0 at x is equal to L. So we do that, v equal to 0 at x is equal to L. So a0 is already 0. So we will get a1 into L plus a2 into L square, because we are now putting x is equal to L in the approximate solution for v. So a2 into L square is equal to 0. So from this expression, you will get, say you can express any one constant in terms of the other. I am writing say a1, so a1 would be equal to minus a2 into L. So you will get some kind of a relationship between the two constants. So now ultimately a0 is 0 and a1 is expressed in terms of a2. So ultimately left out constant would be only a2. So then from based on this, we can say that finally the approximate solution v equal to, now a0 is 0, a1 is minus a2 L into x and plus a2 into x square. So maybe you can take a2 common. So then you can write this as x square minus lx. So this is the approximate solution. Now we want to know this is the approximate solution after satisfying the essential boundary conditions. So finally, of course, you are left with only one constant here, a2. So sometimes this is also referred to as a single parameter solution. That means finally the parameter which we are determining from the big form is a one parameter. So this is referred to as a single parameter solution, a single constant solution. Although initially we started with three constants, but two constants are eliminated based on the essential boundary conditions. So finally this is a single parameter solution, you can say. Now we want to find out a2 by satisfying the weak form. So that means we will have to substitute this approximate solution in the weak form. So you need to differentiate this. So the dv by dx from this expression would be a2 into 2x minus L, and d2v by dx square would be simply equal to 2a2. So as you can see from this, and let us use the, as I said, you could either use Galerkin method or Petro-Galerkin method. So we can use any, we of course in the, when we are using weak form, we cannot use the method of least squares or collocation method, but we are basically using the essentially we are using Galerkin method, either Galerkin or Petro-Galerkin method. Only thing is, suppose, of course, in case of Galerkin method, the weight function is already decided based on what approximate solution we assume, in this case this one. But if you are using a Petro-Galerkin method, then you'll have to make sure that the weight function is differentiable twice, because in this integral term you see second derivative of w, so we have to assume an approximate, the weight function in Petro-Galerkin method, which is differentiable at least twice. So that's the criteria you will have to use. So I am going to use Galerkin method over here. So as per the Galerkin method, now the weight function is taken as, so what would be weight function here now? Yes, anybody? Yes, yes, please. Any answer? What would be the weight function? W. Hello, am I audible? Hello, am I audible? Yes, am I audible? Yeah, I think I am able to hear you.
Yes, sir, you are audible, sir.
Okay. So I was just asking what would be the weight function for this case if we are using Galerkin method. See, this is the approximate solution which I have listed over here. Eh,
Sir, x square.
Yeah, say again, please. Say again, please. See, the weight function is the coefficient of unknown constant in the approximate solution.
So x square minus lx.
Yeah, x square minus lx. Thanks. So w will be x square minus lx. So that is what is going to be the weight function in this case. So now if we substitute this in the weak form. So if you look at the weak form, the first, if you look at this set of terms. So now if you look at this one, so this term is has to be evaluated, the boundary term. So it has to be evaluated at x equal to 0 and L. So now if you look at your weight function, we do not know about this d by dx ci into d2v by dx square. This is actually shear force. So we are treating that as an unknown. So but what about w? So if you look at w, because at these two ends the corresponding variable v is specified, so we will not know what is the value of shear force. So we look at the values of w. So if I put x equal to 0 in this expression for w, so we will get, sometimes depending on the problem, this could be non-zero also. So you have to keep that in mind. But the way I'm evaluating, so that is what is more important. So now if we put x equal to 0 in this w, it is actually 0. So this term at x equal to 0, this particular term, whole term at x equal to 0 will be 0. Similarly, in this expression, if we put x is equal to L, so we will have again a w equal to 0. So this term at the lower boundary x equal to 0 as well as at x is equal to L is actually 0, because w is 0 at both x equal to 0 as well as at x equal to L. So we will have, when we look at the big form, so first term is 0 at lower boundary and it is also 0 at upper boundary. Then we have, now if you look at the second boundary term, this particular term, so we have seen in the boundary condition. Now see, as far as the essential boundary conditions are concerned, we satisfy them before substituting the approximate solution in the weak form. But now comes the natural boundary conditions. So we know that at both x equal to 0, dv by dx is 0, and at x is equal to L also dv by dx square is 0. So this term is 0 at both upper boundary as well as lower boundary. So therefore this will also be 0. So you will get essentially minus 0 minus 0. So that is what we get from the first these four boundary terms, two from here, two from here. And then the third term, if you look at what we have over there, so that is integral 0 to L and d2w by dx square. So now if you look at similarly d2w by dx square, it is actually going to be 2. So that is 2. Then ei and d2v by dx square, which is 2a2, and then dx. So this is the this term here. What we have, d2 w by dx square into ei into d2 v by dx square. So that gives you basically this, and then we have minus integral 0 to L w, which is x square minus lx, and into q dx, and this whole thing equal to 0. That's your basically the weak form. So now if you look at the integral of this term 2ei to a2, so whole thing is a constant. So this integral is going to be simply L. So we will have 4ei L into a2. That will be the first term. Minus, we will look at the integral. We are taking, keep in mind here that we are taking ei and q as constants. Suppose if they are functions of x, so we, whatever function of x they are there, ei and q, we put those functions and then you'll have to carry out the integration. So if you, even if you have beam with variable ei, you can solve the problem exactly in a similar manner. Only thing is, suppose no, for half of the beam flexural rigidity is, let's say, 2 ei, and for other half it is ei. So then you split this integral into two parts, 0 to L by 2, where you put ei as 2 ei, and from L by 2 to L, where you put ei as simply ei, and carry out the integration. So the solution will be exactly in a similar manner. So maybe q may be variable also, so you do the similar manner, the q function also. So when you integrate this, so we will have minus q, and then here integral of x square is x cube by 3, and when you put the limit it would be L cube by 3, and minus Lx, so integral of x is x square by 2, and when you put the limit, so it would be L cube by 2 equal to 0. So now if you see this a2, you will find that a2 would be equal to, from this equation, now you can simplify. So it would be minus ql square upon 24 ei. So therefore finally the solution will be, if you look at the solution, so solution is v equal to a2. So let me take the minus sign inside, so it would be ql square upon 24 ei, and then we will have lx minus x square. So this is the approximate solution for this problem. And you can actually calculate, say for example, the deflection, maximum deflection, which would be at center. So if you look at the v at x is equal to L by 2, so that you can get as ql square upon 24 ei, and then we have this as first term would be L square by 2, x is equal to L by 2 minus L square by 4. So this will become yeah, 2L square minus L square, so L square by 4. So we will have q ql is ql power, yeah, ql power 4 upon 96, yeah, 96 ei. So this is the value of deflection at center. So although, no, as you know, the differential equation is a fourth order differential equation. When we try to find out its exact analytical solution, that solution is going to be in terms of x cube, for no, x power 4 rather, no, not x cube, but it would be in terms of x power 4. But based on this quadratic solution itself, we are able to get the deflection at the center, which is actually accurate, because you get the deflection ql power 4 upon 96 ei. If you try to find out the exact solution. So this is what we are able to do. Now as a home assignment of what you have to do yourself is the another level of approximation is, rather than, this was a minimum polynomial which we can assume in the approximate solution, that is a0 plus a1 x plus a2 x square, but you can add one more term, So other is this part is done, of course, that when you go up to this, you are done. If you are asked to find additional quantities, you can do that. But next level of approximation could be that we take a cubic polynomial, or we take a quartic polynomial up to x power 4. So those are the various levels of accuracy we can actually improve. So a next level is a2 x square plus you can have a3 x cube. You can just increase one more term. So now you have got four terms, although this will still not be an exact solution of this problem, because exact solution would involve terms up to x power 4. So that also you can do. But let's say we want to work with this initially the four terms in the approximate solution. So we will eliminate some of these constants through the boundary conditions. So one, we know that v equal to 0 at x equal to 0, so that will as usual will give you basically a0 equal to 0. And another condition is v equal, these are the essential boundary condition at x is equal to l for the same problem. So this will give you a0 is already 0, so you'll get a1l plus a2l square plus a3l cube equal to 0. So again what you can do is you can express one constant in terms of the other, so you can easily do that. Now you can express a1 in terms of a2 and a3, so you can write minus a2l minus a3l square. So that is what you will get. So now if a0 is 0 and a1 is minus a2l minus a3l square, then the approximate solution will satisfy all the essential boundary conditions. So then once you put this, you can write v equal to a0 is already 0 and a1 is no minus a2l minus a3l square and whole thing into x, plus we have a2x square plus a 3x cube. So that is what we have. So now you can see, you can combine the terms together. So you have a2 and we have x square minus this term is the a2 term, so minus lx, and plus now you can have a3 is x cube minus this term which is l square into x. So now if you have this solution, this satisfies your all the essential boundary conditions. So that is v equal to 0 at x equal to 0 and v equal to 0 at x is equal to l. So it satisfies all your essential boundary conditions. And after satisfying the essential boundary conditions, see, this is because we are using weak form. So that is why we are just trying to satisfy the only essential boundary conditions a priori. Now if we it was original weighted residual statement, then we have to satisfy all the boundary conditions. So we'll also have to make sure that d2b by dx square is 0 at x equal to 0 and l. So no, because this is only the solution based on big form, so we are trying to satisfy only the essential boundary conditions. And after that we have this solution which is involving two unknown parameters. So a2 and a3 are unknown constants. These have to be determined based on the by satisfying the weak form, and for that we need to choose the now weight function. So now in this case, how do we choose the weight function? So now the weight functions will be again, let us say we want to use Galerkin method. So now there are two unknown constants, a2 and a3. So we require two set of simultaneous equations. So that means those two set of simultaneous equations can be generated using two weight functions. So one weight function w1 will be coefficient of a2. So that is x square minus lx. And the second weight function would be w2, which is coefficient of a3, the second unknown constant. So that is x cube minus l square into x. So these are the two weight functions. And so now remaining thing I want you to do this. So remaining part you should do as a homework problem. So set up the two equations in terms of a2 and a3, and then solve those equations for a2 and a3 and see what you get. The next level of approximation could be, we take the 5-term solution initially in terms of a0, a1, a2, a3, a4, and eliminate two constant using essential boundary condition, and then you will have three unknown constants to be determined. So you will have three weight functions, three set of simultaneous equations, and will be solving for a2, a3, a4 in that case. So you just at least try to solve this problem the way we did. The only thing is, I think earlier, if you remember, I had done a problem with two weight functions for a rod with axial load. So the same approach you can follow and try to set up the equations and solve for A2 and A3 in this. So this is a homework problem, and you must do all whatever I'm saying, no? Because some or the other point of time you will have to use these to solve this. So yeah, this is yes, basically the solutions based on the weak form directly. Now, one of the most popular approach and powerful approach in solid mechanics problems is what we call as Rayleigh's method, which is based on the minimum of total potential energy. So although most of the problems, and of course in all, you can say in all solid mechanics problems, you can always write the total potential energy expression, which would be consisting of strain energy and potential of external forces. So you can write that directly. But no, if we are given a differential equation and we want to obtain that, so that is what is I'm going to discuss next. The topic. So we call it that total potential energy functional. In general, we call it as integral functional. So next, I am going to talk of the integral functional. And once we have done with the integral functional, then I will also discuss how to use Rayleigh's method to find out the approximate analytical solution. And after that, we would actually be moving formally to finite element method. So we will be using some of these techniques to develop the finite element level governing equations, and we would be taking different problems and solving them. So next is integral functional. So these are the basically what I am discussing is the basic concepts. So now the integral functional, so how we get it. So integral functional, as I said, one is directly for solid mechanics problems we can write. We know how to write down the strain energy and how to write down the potential energy of externally applied forces, and from that we can write directly. But what we are interested in here in that, if we are given a differential equation, then how to obtain the corresponding equivalent integral functional. So solution of the differential equation is essentially equivalent to minimization of the integral functional. So this is, we are trying to do this for a given differential equation. So when I am saying this given differential equation, so again idea is through the, I'm going to explain this through the examples. So I'm going to take the rod problem. So what we did earlier. So there are, of course, the boundary condition can be anything. So it has, so this distributed load Q, and this is a coordinate X here, and the displacement in this direction is L. And for a general case, let us say there is a force here which is Q naught, and there is a force here which is QL. And this whole thing is, so we know the know the differential equation for this problem, and we already have written the weighted residual statement. So we know that weighted residual statement is W, and then we have d by dx of EA into du by dx uh, plus Q dx equal to 0. So this we have said. Now this is the differential equation, d by dx a du by dx plus q equal to 0. So here what you have is u, the first derivative of u. So now this is the weighted residual statement. So we already know that this is the weighted residual statement. Sometimes we write it in abbreviated form as WRS, weighted residual statement. And we have also derived its weak form, so I am directly writing. So the weak form is W, and then we have EA du by dx, the whole thing evaluated at 0 and L, minus integration 0 to L dw by dx into EA into du by dx dx, and plus we have integral 0 to L w q dx is equal to 0. So this is weak form. We already know this now, that this is the weak form of the given differential equation. So now what I am going to do is, let us say that EA into du by dx at x equal to 0 is q naught. So let EA, that is no, du by dx is the strain. When you multiply by Young's modulus, it gives you stress. When you multiply by cross sectional area, it gives you axial force. So EA into du by dx at x equal to 0 is, let us say, this force q naught. So essentially EA into du by dx is nothing but this force q naught. And let us also take this EA into, this is a secondary variable EA into du by dx, and that secondary variable I am using some notation q naught and ql. So let us say this is ql. Additionally, most important thing, when we want to go, so we have a know how the procedure for finding out the integral functional is that first we write the weighted residual statement, then we obtain its weak form, and once we have got the weak form, so at the boundaries, we write the secondary variable, using some notation. So in this case, I am calling it as Q naught and QL. And additionally, we take the weight function as variation in U. So that is the most important thing. So, and the last third thing is that let W, the weight function W will be equal to delta U. So this is actually exactly the Galerkin method. So in the Galerkin method, if you see what we are taking, the weight function, they are coming from delta U essentially actually. So what is delta U? So this symbol delta is a variation symbol. So this is referred to as variation of U. And now what is this variation? I'm going to just explain. And delta is known as variational operator. So like d by dx is a difference derivative operator. So similarly delta is a variational operator. And what is delta u? Delta u is variation of u, as I have written over here. And what is this variation? What is the characteristics of this variation? So delta u is the variation in displacement. What it is? So I'm just writing the properties of that. So one thing is that this variation in u has to be kinematically admissible. So I will tell what I know what these terms mean. Kinematically admissible and infinitesimally small, and then instantaneous, and the last thing is that it is virtual displacement. So the variation of u is a quantity no is a virtual displacement which is kinematically admissible, infinitesimally small, and instantaneous. So this is what the virtual displacement actually means. So now what it actually means, what you mean by variation. So let me explain through the graph. So let us say that we have u is a function of x. As you know that already, u is a function of x, and this side, so we have u, and this side we have x. Now a given problem will have essentially some boundary conditions. So let us say the boundary conditions are at x equal to 0, u is 0, and at x is equal to L, du by dx equal to 0. So let us this graph I am drawing for this case, although I started with a general problem, but graph, as far as graph is concerned, so this is the rod, this load is q, and this origin is x here, and in this direction is the u. So we know here at this location that u is 0, and at this location we know that du by dx equal to 0. So first term which is written is kinematically admissible. So if at x equal to 0, u is specified, then delta u has to be 0 there. So it should satisfy homogeneous form of the essential boundary conditions. So kinematically admissible means no, the variation of u should satisfy homogeneous form of essential boundary condition. So let us say no you know the actual solution, or say the exact solution of the problem is something, some function of no L like this. So this u is basically the exact solution of the problem. U, this is exact. Then what we do is we look at the varied solution. Varied solution means in that we add a small quantity virtual displacement. So the virtual displacement has to be kinematically admissible. So at x equal to 0, u is 0, so delta u also has to be 0. So a u plus delta u would be 0, but it can have any variation like this. So this is your u plus delta u, where delta u is the virtual displacement. Virtual displacement means it is not real displacement, it's a mathematical concept, it is kinematically admissible. So now if I plot delta u, so delta u you can see is something like this. So it is now going something like this. So this is your delta u. Delta u is 0 at x equal to 0 because there u is specified. So it has to satisfy the homogeneous form of essential boundary condition. It is arbitrary, in the sense that it can, we can take otherwise any value, and it is infinitesimally small, so it's very small quantity, and instantaneous, so it's a one particular time instant. It is not that due to change in time this is the variation. The variation is at a particular time instant. So now to obtain the big form, we take w, the weight function, as delta u. That is, the delta u is the virtual displacement or variation of u, a variation in u. And variation in u is kinematically admissible. That means it satisfies homogeneous form of the essential boundary condition. It is infinitesimally small, so very small quantity. It is instantaneous at a particular time instant, and it is virtual, not a real displacement. So we take this as the delta u, and now, so if we take w equal to delta u, and also make use of this notation, that is a into du by dx at x equal to 0 is q naught, and at x is equal to l is ql. So if you look at the first boundary term, so now I can say, the whatever weak form we have got, so this weak form whatever we have got, we can write the weak form now as the first term, if you look at, is the boundary term, product of two things, w and this one. So at x is equal to l, a into dy dx be denoted as ql, and w equal to delta u. So that u is evaluated at x is equal to l, so I can write that as delta u l, because w is delta u and it is evaluated at x equal to l, so it becomes delta u l into ql. QL is the A into du by dx at x equal to L, minus the same thing evaluated at x equal to 0. So W is delta U. So delta U naught. Delta U naught is delta U at x equal to 0 into Q naught. So that's the one notation I used. Minus we have this integral 0 to L, and then we have d by dw by dx, and w is delta u, so we will have d by dx of delta u, and then we have ea into du by dx into dx, and plus we have the last term integral 0 to l w into q dx. W is delta u, so we get delta u q dx, and this is equal to 0. Now we do one more thing. Actually, when we write the expression for the total potential energy, so we want to take the datum for that. When you specify potential energy, you will always have to choose a datum, because it is not as absolute quantities with respect to some reference configuration, which is referred to as datum. So we want to write the finally the integral functional, which is a total potential energy, as the with the datum as the undeformed configuration, then this integral term should be positive. So then what we do is we multiply whole equation by -1, so that the third term is positive. So multiply the whole equation by -1, so that the third term is positive. And this is to take the datum for the, this is to take, so this integral term basically we want to make it positive, so that is what we, our aim is to take the datum for potential energy as undeformed configuration. Undeformed configuration means when you start applying the load, so initially it is there in the initially undeformed configuration, so we want to take that datum and based on that we want to write the finally the total integral total potential energy, functional or integral functional. So now if you do this, so then what we can do is the then this term will become negative, this term will become positive. So we will have basically delta u naught into q naught minus delta ul into ql. That third term will become positive, so we will have integral 0 to l. Another important property of this variation is that this variation and the derivative operator, they can actually be interchanged. So this term, as you see here, I can also write that as delta of du by dx. So either first you differentiate x with respect to, for, either you first differentiate u with respect to x and then take the variation, or first take the variation of u and then differentiate it with respect to x. Both will be same. So I can write this as ea into du by dx into dx, and then last term would be minus integral 0 to L delta u q dx equal to 0. So this is what you will have. Now what we want to do, actually if you see this variational operator delta, this variational operator delta is there in all the terms. Now here you have delta, here you have delta, in this term you have delta, you have this delta here. So we want to take this delta common. So we want to, when we want to take this operator delta common, so we can write, no, I can write this delta and inside. So one more thing is, although if you see when I'm taking delta common out, this what I will have inside is say something like u naught into q naught. But in this, q naught is taken as a known quantity, so its variation is basically 0. So we will have, when you use the similar to product rule for differentiation, when you write a delta of u naught into q naught, it would be delta u naught into q naught plus u naught into delta q naught, but delta q naught would be 0 because we are treating that as a known quantity. So that is why we can write it like this, and the second term would be ul into ql. And when I look at the third term, now this one, so you see that this is delta du by dx a into du by dx. Now this u is an unknown function of x, and so also its derivative du by dx is an unknown function of basically x. So when I want to take this delta common from this term, so I have to write half integral 0 to L, and then EA of course is a known quantity, so its variation is 0. So here I will have half of du by dx whole square dx. So that is what I will explain you a bit analogy to differentiation, so how we are getting it. So now if you as I said, when you are operating delta onto these two terms, when you apply the product rule, you will get delta u naught q naught plus u naught into delta q naught. Delta q naught is 0, so you get essentially this term. When you apply the product rule to this, so you will get delta ul into ql plus ul into delta ql. Delta ql is 0, so you essentially get this term. And same way, when you apply now delta to this term, EI is a constant, so its variation is 0. Constant means it's a known quantity. So EI is a known quantity. It could be function of x, but it is known quantity. So its the variation delta EI is 0. So you will have delta of basically du by dx whole square. Delta of du by dx whole square would be twice du by dx into delta of du by dx. So you will exactly get this term what we have here. and then the last term integral 0 to L, delta you are taking common, so u into q, because where q is a known quantity, so its variation is 0, so you will get directly this dx, and this whole thing is equal to 0. Now as I was telling you, so I have already explained you. Now let me tell you one by one. So if I do delta of u naught into q naught, so what do we get? So we get delta u naught into q naught plus u naught into delta of q naught. But this q naught is actually equal to 0. As I said, q naught is a known quantity. We are taking it as a known. So variation of a known quantity is always 0. So similarly, if you look at delta of UL into QL, so then this is exactly the term what we have got over here. As you see over here, the second one, if we take UL into QL, that would also be delta UL into QL plus UL into delta of QL, and again this is 0, so because we are taking this as a known quantity, so that gives you basically the second term. Now the third one, what I am saying is, when you take the variation of delta of this half integral 0 to L EA into du by dx whole square dx. Now if you look at basically this term, so we can write this as I said, variation, integration, differentiation, they are interchangeable. So this variation operator can be taken inside. So half, I can write integral 0 to L, then I can say delta of EA into du by dx whole square dx, plus I can write half integral 0 to L. I am using product rule. EA into, then we have delta of du by dx whole square. So yeah, this is what you will have, right? And as I said, we are using the interchangeability of variational operator delta and the integral and derivative operators over here. So now this is equal to, as I said, this is 0. Why? Because EA is a known quantity. We know priori that what is Young's modulus, what is the material of the rod, and what is its cross sectional area, how it is varying. Although no, they could be functions of x, but they are known, so their variation is 0. So then what we will have is left with half integral 0 to L EA into delta of du by dx whole square dx. So this is what we will be left with. Now half integral 0 to L EA, when we write this delta, so now if you look at, like d of x square, if you write, so it would be 2 into x dx. So exactly, no, d of x square means d by dx of x square if you write. So I think let me explain it from there. Probably it is easier to appreciate from there. So you know that d by dx of x square is equal to 2x. So you can say that d of x square is equal to 2x dx, isn't it? So similarly, this variational operator delta also goes exactly the same way, but it is not derivative operator. No, that you have to keep in mind, that it is not a derivative operator, but it operates like no derivative operator, d by dx. So now delta of du by dx would be twice of du by dx into delta of du by dx, exactly the way you have d of x square is equal to 2x dx. So same way I have written 2 here, and then now in place of x, you have here du by dx, so du by dx, and then delta of du by dx, and then integral of course d by dx. So finally the half of gets cancelled, and then you can write this as integral 0 to L EA, and of course you can write any one term, this as first and this as at the end. So delta of du by dx into du by dx or dx. So we will see exactly why I wanted to tell you that when we operate delta to this term, we exactly get this one. So because why I am saying that, because we are taking this variation operator delta common. So when we take delta common and when we again take this delta inside, we should exactly get what we have over here. So we are correct. And the last term is, now you have is this delta of integral 0 to L u q dx. And now if you look at this, so we can take the delta inside. So integral 0 to L delta u q dx plus integral 0 to L u into delta q dx. And now since q is a known quantity, so this term is 0. So you have essentially integral 0 to L delta u q dx. So that means what we have written here. I just wanted to explain you that how we are taking out the variational operator delta common, and when we again operate it inside, we get exactly the same term. Now this big form what we have. So we get exactly the same thing. Now what I can write now if you look at this particular expression, so is it clear what I have explained? Yes, any question, any doubt in any of these terms, the way I have explained, or anything, any question? Because this is very important thing, you should understand this. Okay. So then if there is no doubt, so then if we, what I have written on this term, this equation. See, when I am, if I ask you to, I give you a differential equation, and I ask you to derive the integral functional. So you don't have to show these steps, but you should do it correctly. When you take the variational operator delta common, you don't have to write all these steps. This is to explain you that how I have written that. So up to here, you don't have to write, or anybody asks you to gives you a differential equation and asks you to write the integral functional, so you don't have to give all these steps. No, starting from here, you don't have to give these steps. This is just to explain you that how I have written that. So now if you look at this finally that equation, so I can say that equation as delta of I equal to 0. Now this is your essentially the weak form. It is still the weak form, only thing is we have written in terms of delta I equal to 0. So this is your weak form after putting w equal to delta u and taking the variational operator delta common. So now here this I is what is known as the integral function. So now I is equal to what is there inside, no, here you see here we have taken this delta, and this whole thing I'm referring as I, this term, this term, this term, and this term, this put together whole thing is referred to as integral functional. So q naught into u naught minus ql into ul plus integral 0 to l ea into half, of course, is there, half du by dx whole square dx, and minus integral 0 to l u q dx. Yeah, so this is known as integral functional. Integral functional. We also call it as, in the solid mechanics, we also call it as total potential energy. So now another thing which remains is to explain you physically what these terms mean. So now out of this, the first term, not the first and second, let me first take the third term. So third term is actually strain energy. So I can usually, what we do is, of course, we write the strain energy first and the other terms later. So you can write anywhere, any term, it really doesn't matter. So now let's talk of the physical interpretation. Physical interpretation of terms of I, that is integral functional. So let us take first the third term. Now the third term is nothing but strain energy. So let me tell you how it is strain energy. So I hope that you know this term strain energy. So usually we denote the strain energy by pi. So pi equal to, now this rod problem, if you look at, is a under uniaxial state of stress. So uniaxial state of stress means sigma xx is non-zero, and sigma yy, sigma zz, tau xy, tau yz, and tau zx, they are all the stresses are zero. And if you look at the strains, epsilon xx is independent and non-zero. Epsilon yy and epsilon zz using Poisson's ratio can be expressed in terms of epsilon xx, and gamma xy, gamma yz, and gamma zx are zero. So if you look at the strain energy, which is half integration over volume, only non-zero product is sigma xx into epsilon xx. Of course, this is a linear. We are assuming, when we have derived the differential equation, we have already said that the material is linear elastic isotropic. So the strain energy is sigma xx into epsilon xx dv. This v is volume. This is volume. So I think I am assuming that the strain energy for a linear elastic body can be written as sigma xx into epsilon xx, half of sigma xx into epsilon xx. So half of sigma xx into epsilon xx is strain energy density, that is strain energy per unit volume, and when you integrate it over the total volume of the body, you get the essentially the total strain energy. So now this is the starting point for the strain energy, half of sigma xx into epsilon xx and integration over volume. And then the integration over volume can be split into two parts: integration along length 0 to L, and integration over the cross sectional area. And then sigma xx is nothing but E into epsilon xx for linear elastic body. So sigma xx is E into epsilon xx into epsilon xx, as dv, as already said, can be written as dA into dx. So dx is along length and dA is the cross sectional area. Product of two will give you the differential volume dv. And then this is equal to half integral 0 to L integration over area. And we know that epsilon xx is du by dx. We are taking a small deformation gradient, so strain can simply be written as du by dx. So this is epsilon xx square, so you will get du by dx whole square dA dx. So now if you look at, in this term, E is, we are assuming that it is independent of the cross-sectional coordinate, and du by dx is only function of x. So the integration over a cross-sectional area will simply give you the area. So it would be half integral 0 to L. You will have EA into du by dx whole square dx. So now you see, this is the third term. If you look at, is nothing but exactly the strain energy. So third term in the integral function, although we wrote that from the differential equation, we arrived at this integral function, all this whole thing from the differential equation, but the interpretation of this third term is that it is nothing but the strain energy stored in the rod. So third term is the strain energy density, as I already explained you. Now let me look at the fourth term, and then I will come to first and second terms. So fourth term is this one. So now let me explain you the interpretation of the fourth term, what that fourth term means. So again, let me sketch the rod. So this is the rod we are taking under the axial load. So this Q, and x coordinate is over here, and this is U, the total length is Z. So this is no, U is the displacement at any point x. Now let's take a differential length of the rod, say dx. So this is the dx. So if you look at the force over this differential length, because Q is force per unit length, so the total force over this differential length is going to be Q dx. This is the total force, that is Q is the force per unit length, and then we are multiplying by this length dx, so we get the total force. And now we multiply this total force with the displacement at this point. U is a function of x, so it's a displacement U at this point is, let's say, simply U, which is a function of x. So now this is displacement, force into displacement. This is force and this is a displacement. So the force into displacement is what? Work done. And work done, negative of the work done is actually the potential energy. So if we multiply this by minus, we get the potential energy. Now this is the potential energy of the force Q acting over the length dx. If we want the total potential energy, then we integrate it from 0 to L. So you will see that third term is nothing but potential of externally applied distributed force. So potential of externally applied distributed force. So the minus sign is why? Because no, the potential is negative of the work done. So and that means no, when you apply, and the datum for that is taken as the undeformed configuration. Of course, the datum for this potential energy, the strain energy, datum for the strain energy is the undeformed configuration. The datum for this potential of Q is also undeformed configuration. So when the body has deformed by this displacement U, essentially the capacity of the force Q to do work has reduced by this amount 0 to L U Q dx. So minus sign is because capacity of Q to do work has reduced, and that is why there is a minus sign. So potential of this is potential of externally applied distributed force, actually Q. So that's the fourth term. Now if we want to look at the first and second terms, so now the first and second terms, finally let me first and second terms. And for you it is important that you understand, so because most of the time we may not start with a differential equation and then write the integral functional, because for the development of finite element element level governing equations, we will most of the time we will directly use the integral functional. So we will write directly the integral functional, which will be consisting of strain energy and the potential of applied forces. So we should be able to write then directly also, no, the integral functional or total potential energy, we should be able to write directly. So now the last term, if you look at, no, the, as I said, no, when I have taken the rod for this integral functional concept, so I said here this Q naught, here it is actually QL, and this is your x coordinate, and you have of course this U, and of course no, this force Q is there. This is x equal to 0, and this is here x is equal to L, and display, this Q naught force is along negative x direction, QL force is along positive x direction, because these are axial forces, they are positive. Now what is the I think another thing is you would have studied the sign convention for these when stresses and these internal forces. So now if you look at this right side, the outward normal to the cross section is along positive x direction. So the QL is taken positive along positive coordinate direction on a positive phase. Positive phase means the outward normal is along positive coordinate direction. If you look at the left side you have this Q naught, outward normal to this left section is along negative x direction. So the positive axial force would be along negative x direction. So axial force is positive on a negative phase along negative coordinate direction. So what I have shown here, Q naught and QL are the positive axial forces. But if you look at the displacements, so the displacements are here. Let us say the displacement is U naught. No, for a given problem it may be 0 or non-zero, but U naught has to be taken positive along no positive x direction both sides. So here it is, the displacement is, let us say, UL. U is U naught is value of U at x equal to 0, and UL is the value of U at x equal to L, but their directions are same along positive x direction. So now if you look at the finally these terms, so now look at the work done by Q naught. So what would be the work done by Q naught, because this Q naught is the displacement in this direction, and the Q naught is the force in this direction, whereas the displacement U naught is in the opposite direction. So the work done is minus Q naught into U naught. And as I already said, if we take the datum as the undeformed configuration, so then this negative of this is going to be the potential energy of Q naught. So we will have a minus sign over here. Then if you look at similarly the other term, If you look at this ql, the force ql and the displacement ul, they are in the same direction, so their work done is ql into ul, which is positive, and potential is the negative of work done, so we put a minus sign over here. So finally you get this as q naught into u naught minus ql into ul. So this is the potential of in forces, potential of in forces. So you see all the terms which are there in the integral functional I, they have physical interpretation. For this problem, they all can be interpreted. So we could directly also write the total potential energy functional I in consisting of strain energy density and potential of all the forces which are acting in that. So this is the interpretation of all these forces. So this is how the integral functional is obtained. No, for this one particular differential equation. Now let's take another example. So another example, I'm taking this the second differential equation which we have solved using the weighted residual method, where we tried to make the weighted integral of residual equal to 0, and also we tried solving that using weak form. So for that, let us now try to arrive at the integral functional. So next is Euler-Bernoulli beam. So that is actually I know there are assumptions in that differential equation. So I think more about these various assumptions will be when I discuss the finite element, and maybe some part when I do the physical interpretation. So for this we have already seen that the problem we are taking is that this is a beam. It's a kind of the length is much smaller, larger compared to cross sectional dimensions, but it is subjected to transverse force. So the transverse force is actually say q, and this is the x coordinate, this is the y coordinate, and the deflection along y direction is v. So at the ends there could be shear forces and bending moment. So shear force, let this in, they could be zero or non-zero depending on the specific boundary condition, but right now I'm taking a general case. So this is, let us say, shear force at the end is vl, capital V, and the bending moment is ml. And on the left side, the outward normal to the cross section is along negative x direction, so the positive shear force would be along negative y direction, so that is, let us say, v naught, and positive bending moment would be about negative z axis, so this would be bending moment, say, m naught. So this is the whole problem. For this differential equation we already know. So the way, if I write the better residual statement for this problem, integral 0 to L, so W into weight, the d2 by dx square into EI into d2v by dx square minus q dx equal to 0. This is the weighted residual statement. The differential equation is d2 by dx square in EI d2v by dx square minus q equal to 0. That is the differential equation for this problem. So you assume that you are given a differential equation and asked to find out the corresponding integral function. So for this we have already derived the weak form. So the weak form for this problem is obtained by carrying out the integration by parts twice. So we know that w d by dx of ei into d2v by dx square evaluated at 0 and L minus you have now I am directly writing after the two steps, because we have already derived this dw by dx ei d2v by dx square evaluated 0 and L plus integral 0 to L d2w by dx square into ei into d2v by dx square dx and minus integral 0 to L wq dx equal to 0. So this is the weak form. We have already derived this, and we have also used it for solving, finding out the approximate analytical solution. So this is weak form. Now so we want what? We want to find out the integral functional for this problem. So again what we do is we take the weight function as delta v, variation in v, the unknown displacement. So for that purpose, let w will be delta v, variation in, now the unknown variable is, the reflection is v. So w, the weight function w is taken as delta v. So depending on the problem, we take delta v. And also the secondary variables, that is shear force and bending on, let me also write in terms of the notations we have used. So minus d by dx of ei into d2v by dx square. Suppose no, you don't understand why minus sign, so you can also put plus sign and you assume, but you should explicitly write that, and no, then it is also correct. Now, if I don't use minus sign, then whatever you do, that is also correct. Only thing is sign of those terms will be different. So that is at x is equal to L is, let us say, VL. This is capital V. So keep, make sure that understand the difference between this small v. This is the deflection v in the displacement along y direction, and this is the shear force v. So this is the shear force at x is equal to L. And similarly, say minus d by dx of ei into d2v by dx square at x equal to 0 is v0. And then you have in the second boundary term, the secondary variable is this ei into d2v by dx square. So we are also going to denote that by these letters. dv by dx square at x equal to L is, let us say, ml, and ei d2v by dx square at x equal to 0 is, let us say, m naught. So once you have done this, so then let's look at what we can get from the big form. So now the minus sign I have already introduced. So as you say over here, see over here. So the first boundary term is again consisting of two terms. One is the upper boundary, another is at the lower boundary. So the lower boundary would be minus with a minus, and that minus is absorbed in the definition of shear forces. So, and W is delta V. So you would see when I look at the big form, so the first term, the lower boundary term, can be written as delta of V naught into V naught, capital V naught. So minus d by dx ei d2 v by dx square at x equal to 0 is V naught, and into delta V naught. At the upper boundary, because we are introducing the minus sign here, so we will have another minus coming over there. So we will have delta VL into capital VL. Then coming to the second term, already there is a minus sign over here. So when I write the lower boundary term, minus minus will become plus. So that will become basically plus delta of dv by dx, because w is delta v, and there we have dw by dx. So I'm taking delta out, so we can write this is delta of dv by dx at x equal to 0 into m naught minus the upper boundary term. We will have minus sign there, minus dv by dx at x is equal to L into ml. So these two boundary terms, this term and this term, will give you these four terms. And then the last term is, the next term is integral 0 to L. We have d2w by dx square, and w is delta v. Delta and d2 by dx square are interchangeable, so we can write that as delta of d2v by dx. This I can write as d2v by dx square ei into d2v by dx square dx. Minus, we can write this as integral 0 to L delta v q dx equal to 0. Now what you have to do is you have to take this variational operator delta common. So I think I want to stop here, and this also you try, from this you try to get the integral functional I, and also try to do the physical interpretation. Of course, we will discuss that in the next class. So I want to stop here, and if you have any questions and doubts, now you can ask. So are there any questions, doubts? Anybody? Okay, so if there are no questions and doubts, I am stopping here. Thank you all for your attention.